Good evening. It's a great pleasure to have you this evening on the CalTech campus. And welcome to, I think, seminar number 2 of the Anne Rothenberg seminar series at CalTech. As some of you may know, CalTech trustee Jim Rothenberg and Anne conceived this idea of a seminar series as a way to expose some prominent leaders of the community to ongoing research at CalTech, exciting things going on at CalTech. And when they talked to me about it, they said they would like it to be small events with invited guests, a very small group. And so we have a small group tonight. There are a few more people who are going to join us, I believe, in a few minutes. And Jim himself will be a bit late, but will join us. And the idea is to bring us a small group of interesting people and leaders in the community, and to have them exposed to some exciting work ongoing on the CalTech campus. And it will be followed by a reception and a dinner where, because of the size of the group, you will be able to engage the speaker and argue and all those good things that I'm sure you are very good at doing. So thank you again, Anne, for your support. We're here because of you. So I'm going to introduce our speaker for the evening. It is Dr. Nate Lewis. And Nate has been on the CalTech faculty for almost 20 years. Time does fly, Nate. I've been here for 1 year, and 1 year disappeared. But, he received his first 2 degrees from CalTech, and then for a while got some additional practical training by going to MIT, and he's received his PhD at MIT. Started his career at Stanford. And he joined in 1988, he joined the chemistry faculty at CalTech. And he's currently the George R.G. Ross Professor of Chemistry. He is in charge of a fairly large research group, which is dealing with sustainable energy research, and you will hear more about it today. In addition, he has served as a principal investigator of the Beckman Institute Molecular Materials Resource Center at CalTech for 20 years about. He has been a Sloan Fellow, a Dreyfus Teacher, and a Presidential Young Investigator awardee. He has won many, many awards in his field and has published a large number of papers. And he's now more and more known in the country as the go-to guy when you want to talk about energy, especially sustainable energy. And he's advising governments, industries, academics, the press, and even people like us. In fact, to tell you how busy he is, I believe he's going to leave us tonight just after dinner and take a red-eye flight to Washington, where I think he's making a presentation at the White House tomorrow morning. So tomorrow he will be with the real president. Okay?
Won't be the real president.
Now, in fact, if you want to hear more about what Nate is doing and some of his colleagues, in addition to tonight, in a few weeks there will be a special on PBS called Curious, with a number of research programs being outlined, and all those research programs are at CalTech. It was a 2-hour show on PBS on science. And all of the examples of science are coming from CalTech, and one of them is the work being done by Nate. I think the show will be on TV locally in Los Angeles on KCET for the first time on November 15 at 9 o'clock. So if you want to learn more after tonight, 9 o'clock, November 15. Nate, it's a pleasure to have you.
Thank you very much for that kind introduction. We were actually also on TV on 30 Seconds on Nova about a month and a half ago in an episode they produced here called Saved by the Sun. That was notable because it was broadcast against American Idol, the #1 rated show on TV. And so I'm sure there weren't 10 people in the city that actually even saw it. But it is there in principle on tape, so you could go back and look at it again. I'm delighted to be here, and I'll try to give you a feeling for what we do. And the reason is that, scientists and engineers that are doing interesting work, the general public doesn't fully understand that we can do anything in the sense that we can choose what we want to do. Some of my colleagues want to work on helping to cure disease, and they're very good at that, and they can get funding to do that, and it's a wonderful thing to do. Others can work on improvements in technology and how we'll get new coding across the internet, and they're terrific at that. Others work on ways to predict and measure earthquakes and ways to peer into the heavens and see through our great telescopes. Others, like myself, choose to work on energy. And then the question would be, why? Why do we care about energy, given that we actually have a lot of cheap energy? And given all the things that we could do, why are some of us so passionate about actually working on renewable energy? And if you could choose, what should you work on? Shouldn't we just build cheaper windmills, or shouldn't we just find easier ways to pump oil out of the ground? What do you work on if you care about making a difference with what you will eventually do? And why should energy even be important? Given that now oil's expensive, but it wasn't that expensive 3 years ago, and still, if you look at your budget, as a family, it's probably 5% of your expenditures are energy. It's too cheap to worry too much about. If it cost us a lot of money, we would actually go and change our light bulbs, and we would save energy because we'd save money. And so the fact is, it doesn't cost us nearly enough to really worry about much yet. So why should we care? Well, I'll tell you why we should care and what we should do about it, and how people like myself are going about trying to do things about it. So this talk is lovingly called Powering the Planet. Why not? We don't want to talk about power Pasadena. We need to power the whole Earth. The reason we need to power the whole Earth is because not even so much the industrialized countries where energy is really our currency. We can't do anything without it. We can't drive to work. We can't do work. We can't turn on the lights. We can't turn on our computers. We can't eat without it. We can't refrigerate. But it's even more important for the 2 billion people that don't have electricity, and their school children only study at night as long as the 2 candles that they have can light themselves. Or the people that can't purify water and they can't drink it because they have no energy to do it, and they can't cure disease. Energy makes all this happen. In fact, if you look at and you ask a church group to list the top 10 problems in the world, they'll say poverty correctly, and disease, and war. And then you say, how do you fix those things? And immediately, the one thing that rises to the top of the list as the enabler, many people think we just fought a war over energy. Many people think you can't cure disease without a way to get people the ability to take the medicines, which takes energy, or purify their water. You can't cure poverty without it. It's been shown many times that energy tracks economic development. And on and on. Energy is the enabler of all these other things, and no other one thing goes to the top of the list that can fix so many things except clean, cheap energy. That's why we work on it. But we don't have a problem right now. Our problem isn't that we don't have enough cheap energy, really. And so why is it in the news now every day on Google? Politicians talk about it, except in candidates' debates when they don't dare mention it. I'll tell you why that is too a little bit later on, because I happen to talk with several of them on both sides of the aisle, and they understand the issues and dynamics of why you can't talk about it in a real public debate. And I'll tell you what the problem really is and what we're doing about it. So there'll be 3 different parts of this. If you want a more detailed version, an hour-long version that has more technical information, you can get a copy off of my website, which is just my initials at caltech.edu. Or you can just Google me and it'll come up. And I give this all the time. The inventor of nanotechnology, Nobel laureate Rick Smalley, testified in Congress that energy was the single most important challenge facing humanity today. Those pretty strong words. Rick believed that. He spent the last years of his life when he became terminally ill, out of all the things he could do, going around the country telling everybody that the only thing that really mattered was trying to solve the energy problem. Chemical Engineering News, our trade journal, said energy is the single most important scientific and technological challenge facing humanity in the next century. They didn't say disease. They didn't say for science, figuring out how the brain worked. They didn't say curing AIDS. They said energy was our problem. Tom Friedman, now a friend and colleague of ours, having visited once and hopefully will visit many more times, has written, what should be the centerpiece of American renewal is blindingly obvious, making a quest for energy independence the moonshot of our generation. Susan Hockfield, when she was inaugurated as president of our East Coast branch, MIT, said, the time for progress is now, but it's our responsibility to lead in this mission because we can't wait. And we need science and engineers involved to help solve it. The thing that makes energy so difficult is that everybody seems to be an expert in it because we all use it all the time. We get electricity out of our wall and we don't really care where it comes from. We just want it to light our lights. But the fact, oh, we got a fly right there. The fact that we're all experts doesn't mean that we understand the scale of which we really use energy, which really allows us or not to think about solutions. You know, what one works at one house doesn't work if you're trying to do the same thing at scale powering the United States always. Now a laptop computer takes about a watt. If you put on your toaster, it's about 1,000 watts. So don't put your toaster on very long because that's about the average electricity. It's 100 watt light bulbs. That's as much electricity on average as your whole house uses, day-night average. So hair dryers and toasters use a lot of energy. You don't want to leave them on for very long. 1,000 toasters or hair dryers is a small-sized jet engine holding a couple people. It's 1,000,000 watts. 1,000 jet engines is 1,000,000,000 watts, a gigawatt. That's a nuclear power plant. Like you see when you're going down to San Diego, there are 2 of them. And 1,000 nuclear power plants is enough to power the electricity consumption on our planet, which is 1 trillion watts. And of course, you can see that places that people have lights and places that they don't. You can see the difference between those that have goods, South Korea, and those that don't have any lights or goods, North Korea. You can see those who use energy and those who don't. Even this 1 trillion watts is only the electricity fraction of our energy, but 80% of the energy consumed by people isn't electricity. It's the heat that we use to heat our houses and cool them in the summertime. It's the gasoline we use to drive to work. It's all the low-grade energy we use to make our steel, to make our products, to move our food from one place to another, to package it. All that takes energy. And if you add it all up, we on average use about 13 trillion watts. So it's nice to talk about a few light bulbs in Fresno. Politicians love to talk about how many hundreds of thousands of gallons of energy we save, but of course they don't tell you that it's a drop in the bucket out of the trillions of gallons that we use. Right? So we need to set the scale. We use 13 trillion watts on average. The United States uses 1/4 of the world's energy consumption. We don't nearly have 1/4 of the people, so we're energy hogs. We use about 3 trillion watts as our average total load. And 85% of that comes from fossil energy, oil, coal, and gas. A little bit comes from hydro. 10% of it comes from biomass, from plants, where people cut down forests and trees like we've been doing since we burnt wood to heat ourselves in caves. That's 10% of our energy. It's just that, unfortunately, all of that is unsustainably burnt, where you're cutting down forests in the Amazon and trees much faster than they can be regrown. The amount that's sustainable is in this total renewables column right there, of a total of about 2/10 out of 13. And then there's nuclear power that I'll talk about later that's 0.9 out of the total. That gives you a feeling for where we are today. Maybe this will change. Maybe we'll run out of oil. The price will go up, skyrocketing up, and some people say we'll have economic panic. Other people say we'll figure it out along the way because as it gets more expensive, we'll just develop other cheaper technology that will come online in the marketplace. There are 2 opposing views. if you add up all the oil proven reserves and divide by the rate at which we burn it now, we have 40 years worth left. If you add in unconventional resources, we have 80 years worth left. If you look at natural gas, we have between 60 and 160 years, and coal, the United States is the Saudi Arabia of coal. We have over 200 years worth of coal. But this isn't the whole story. You shouldn't panic and say this means we're going to run out of oil in 40 years. Because given the rate in the ground compared to its discovery rate, we've had 40 years worth of proven reserves of oil since the day after oil was discovered over 100 years ago. The reason for that is that when it costs you $1 million a day to drill an oil well, if you're a company whose job it is to find oil, you drill enough wells to find 40 years worth, and then you do something else with your money, like give it back to the stockholders, because it doesn't pay on a net present value basis to discover oil you're going to sell 100 years from now, because the net present value of that isn't very high. So it's never been the case that it only is the case that what we have now is all that there will be. If you ask the U.S. Geological Survey how much do they think roughly there is in the ground for humans to get, that's called the resource base. And divided by our current consumption, we have between 50 and 150 years of oil, approximately, to go. But we have 200 to 600 years worth of natural gas, and either good or bad news, we have almost 2,000 years worth of coal. Furthermore, coal happens to be where two of the biggest energy consumers are physically located, at least the United States and China, also Russia. And if we start to run out of oil, we can convert coal into oil. Do we know how to do that? Absolutely. Germany did it in World War II when denied oil by the Allies. They flipped their whole economy on a dime to run off of coal. South Africa does that today when denied oil from apartheid boycotts by the world. They run their whole country by liquefying coal. It also happens to be the single biggest point source of carbon dioxide on our planet, can be seen from outer space. But if your concern is just economic development and getting cheap, low-cost energy to your citizens, we know how to do this. And so if we run out of oil, we can convert gas and coal into oil. ExxonMobil and Shell are spending over $10 billion in just one country, Qatar, right now, to do this with their tremendous reserves of natural gas that they want to liquefy into oil so they can put it into a tanker and ship it to people like us to drive our cars. So we know how to do this. And by the way, if we ever ran out of this, we have enough methane clathrates off the continental shelves. There's estimated to be more than all the oil, coal, and gas on our planet combined. So the good news is not only do we have a lot of cheap energy, we have it for a very long time. And therefore, the price isn't going to go up very, very much. Now, it's true oil's gone up. But it's still true in Saudi Arabia, the cost of pumping out of the ground today is $4 a barrel. We pay $80, and the difference between cost and price is called profit. And that's because there's a spot market, but that's not the cost of getting it out of the ground. So you shouldn't confuse the two. Well, then why should somebody like me care about this? Because I just told you we've got a lot of cheap fossil energy to run the economies of the world for 1,000 years. So I should be doing something else. Right? Well, we can't really make predictions. Now, we think Yogi Berra said this. We also think Yogi Berra didn't say half the things people thought he said. We know Leo Szilard said it. I've actually traced it back as far as Shakespeare, who said, "We know only what we are, not what we will be." That's close enough. So I didn't give a quote here because I didn't want to offend those fans of literature who could trace it back at least that far. But I'll predict things anyway. It won't stop us. I'm going to summarize, because of course you cannot talk about energy these days, although I've been talking about it in this context for almost 6 years now, well before it was popular to think about the fact that when we burn all that fossil energy, there's only maybe one or two really bad things that happen, and those things could involve the gases released when you burn it, which are carbon dioxide. So I need to tell you about why people like me care about this problem. This is a summary from an important paper published by a colleague that I work with now, Marty Hoffert at NYU, in the journal Nature in 1998. And it tells us what the future is likely to bring. Here's the last century with the Industrial Revolution and tremendous global economic growth and population growth. And here's what the next 50 years the United Nations and the Intergovernmental Panel on Climate Change projected as one likely scenario. And we need to think about 50 years from now, 46 years or 7 years from now, the year 2050 or so, as a good year. The reason for that is twofold. One, my kid's in 10th grade. He's going to grow up into 2050, that's for sure. Two is that unlike setting up a website, when you set up a company and 2 years later you can be a Google, in energy, when it takes 40 years to pay off the capital investment and amortize off a coal-fired power plant, what we're doing in the next 5 to 10 years is going to dictate what is going to be on our planet in 2050. So that's not 50 years from now. That's basically here and now. That's a good time to talk about it. Well, people consume energy, and we're going to have more people. You can pick your favorite number. Maybe 9 billion people, maybe 10 billion. Scientists like to use good round numbers, so we'll call it 10, but 9 or 10 billion is roughly about right. We're at 6 billion now. To figure out how much energy we are likely to use in this scenario, it's not just enough to say we're going to save energy per person. We need to factor in economic growth, because energy runs economies. And so let's look at per capita GDP growth. And here's the historical average. It's been 1.6% per year for the last 100 years. And so it's not unreasonable to say maybe the average is going to be about 1.6% again. But of course, this was done in 1992, when no one foresaw double-digit growth sustained by China and India at 7 to 10% a year. All right? The developed countries think 4% is about sustainable. We hope the return on our endowment is greater than 4%, reflecting economic growth in our country. No country has a policy against economic growth, so it's unlikely this number is going to go negative and we'll go into global depression for a century. So we'll pick the historical average, but I argue that's pretty conservative. Well, if we did nothing else, this rate of population and feeding people and getting them energy, plus economic growth and fueled by energy, would lead to a tripling of energy demand from the 13 trillion watts that we use now to almost 50 trillion by the year 2050. But we can mitigate that because we save energy per unit of productivity, GDP. In fact, we've been saving at a rate of about 1% per year. Now, the developed countries are saving more rapidly than that. The United States actually saves at 2% per year. But the developing countries don't have the luxury. We can only do that because, of course, we have such a big base and are so wasteful that it's easier for us to save than it is if you only have 2 candles to burn at night. You can't really save much energy. Even if you saved half of what you used, it isn't very much to save in the first place. So the average is about 1% per year. And we'll project that we continue to do that. Now, this won't be easy because everything to do with energy efficiency, which we must do if we're going to even get close to addressing this challenge with energy efficient light bulbs, natural lighting, zero energy homes, things that we mostly know how to do today, and there's still lots of things like LED-based lights that would even use much less energy than the compact fluorescent light bulbs that we can buy now, are going to be developed. Fuel cells for vehicles, and we'll assume that we continue to do this and stay on this curve. That brings us in 50 years down to this average energy consumption per person of 2 kilowatts. That's 5 times less energy consumed per person than we currently consume in the United States. So think about what your life would be like if you had to consume 5 times less energy. Let me give you a calibration. Humans at a 2,000 calorie a day diet are 100-watt light bulbs. 2,000 calories a day divided by the number of seconds a day means you are equivalent in thermal consumption to 100 watts. Now, I said we get to consume 2,000 watts per person, but the energy embedded in food the energy to grow the food, the energy to move the food from the farm into the supermarket, the energy to cool it, the energy to get it in your refrigerator is between 10 and 25 times the energy in the food itself right now. So if it's only 10 times, and we hold it to that, 100 watts times 10 is 1,000 watts, and I'm only going to budget 2,000 watts. That means we're only going to budget twice as much energy per person as it takes to eat, as the average energy consumed by every single person on our planet within 50 years. Okay? So it's going to be a tremendous effort to do this, but we'll project that we do that. That'll bring us onto this top curve, because we know how much energy we'll save per person. We know how many people roughly are going to be using that energy and how much economic growth there's going to be. And that means we'll need twice as much energy in 50 years as we use now instead of 3 times as much. If we save more energy than that down to just the level it takes to eat, it still won't matter in the end. I'll tell you why. Because we have plenty of oil, gas, and coal to just meet this demand, and that's what we'll do. China is now building the equivalent of a nuclear power plant's worth of coal every single 3 days to power their electricity in their country. At least that's the stuff they tell us about. It's not clear they even know when a little village actually puts up a kerosene-fired electricity power plant. They only know about the big stuff. In other developing countries like India, electricity is free. It's like water. You know, when a power company puts out the electric wire, people just go string it up to their house. There are no meters. They just put it in like taking water out of the river, right? There's no question that we'll just continue to burn fossil energy is the cheapest way to meet that demand. But you have to be careful what you wish for. You might actually get it. Because there's one other fact. The fact is that we know how much carbon is emitted to the air as carbon dioxide when we burn oil, coal, or gas. Here's the average amount of carbon emitted per unit of energy consumed, again, for the last century. We started out a long time ago being really just bad engineers. You know, burning wood to heat ourselves in caves is just bad engineering because most of the energy just goes out of the cave and doesn't get to the person you're trying to heat. So you make a lot of carbon dioxide emitted to the air per unit of energy delivered to the end user. Then we got better because in the 1900s we went to coal to power our locomotives. But although that's better engineering, it's bad chemistry because coal is mostly one big chunk of charcoal carbon. And when you burn it, you get all carbon dioxide. And so you emit a fraction of carbon dioxide to the air that's defined by the chemical formula of burning coal, which is all carbon, and the heat you get out of that, which you can't change. That's just a law of chemistry. When you burn natural gas, you're better, because that's not all carbon. It's not a charcoal briquette. It's CH4, natural gas. And so you burn CH4 in air, in oxygen. You make 1 CO2 for every 1 CH4. The carbons don't go anywhere. And you make 2 H2Os, 2 waters. So out of the energy you get less CO2 emitted per unit of energy produced when you burn 1 CH4 than when you burn 1 equivalent of all coal, being all carbon. And oil is in between, CH2. So those 3 numbers we can do nothing about because that's a law of chemistry. And because we use roughly equal parts of oil, coal, and gas, in 1990 our average energy intensity was right there. And in the IPCC's projection, they projected that we would continue to decarbonize the energy mix in the next 50 years at the same rate that we had done as our planet historically. And you can see that if we did that, that would bring us down by 2050 to better than a pure natural gas economy. Better means the arithmetic says that if the average emitted is less than that of the best carbon-based source, that you have to have something in there to lower the average significantly. Furthermore, to the extent that you don't just burn natural gas, and I don't think anybody in this room would think that within 40 years we would never burn a drop of oil or a drop of coal again on our planet. If we use roughly equal parts of that, you need even more to get the average down to there. but we'll assume we do this too. So we're going to assume that we're going to do better than a pure natural gas economy and that we're going to save energy so much that we'll get it down to just twice the level that it takes to eat. And if we do that, it brings us to that top curve. The important thing to understand is that that top curve, which is the result of no assumptions, because it just says this is how much energy we're going to use if we save it like we've never saved it before, and this is how much carbon will be emitted as a result of using that amount of energy. We know where it goes in the air. We know how much goes into the oceans. There's no assumptions in this at all. The important point is that that curve is higher than any of these other labeled curves, which would be the emissions that you would want to have if you chose to stabilize the concentration of CO2 in our air at the values in parts per million given by the numbers. For instance, if you wanted to hold the CO2 levels to 350 parts per million, you would have to follow this curve of carbon emissions. That is, you couldn't ever emit any CO2 again from burning fossil energy within 47 years. No oil, no gas, no coal, everything renewable within our lifetimes. If you don't do that, you get higher and higher. Now, we do not know what the consequences absolutely of getting to something like 550 parts per million of CO2 in our air would be, because no human has ever breathed that before. We know from ice core data that the CO2 concentrations have been between 200 and 300 parts per million for at least 450,000 years, and we now have data that says it goes back 670,000 years from ice cores. We also know that swings of about 100 parts per million have been correlated with, every single time, temperature changes that have repeatedly sent us into ice ages. We know that on that trajectory that we'll be, about there within 40 years. We do not know, except in a climate model, what that will bring to our planet. We know what we see. This is 10 years worth of Greenland, summer sea ice melting. We know that if it continues to melt, that there is enough ice there to raise sea level by 20 feet. Scientists are worried about things other than this, though. We're worried about things like this, the permafrost, which is permanently frozen ice that is now melting. In fact, the bubbles in that ice that are being released contain helium that tell us how old they are. And the helium in those ice bubbles is now being released that hasn't been released in at least 40,000 years. The danger here is that as this obviously is melting, it reflects less light because it used to be all white and shiny, and now it reflects less and more gets absorbed, and that releases more melted ice that reflects yet less light in a runaway train effect. There's enough CO2 and methane trapped in the permafrost to not raise the levels by a factor of 2, but to raise it by a factor of 10. This did happen once before on our planet. It happened 230 million years ago, as the geologist will tell you, in the Permian era, when there was a very rapid, on a geologic timescale, release of very light isotopes of carbon into the atmosphere. And that's a telltale sign that it didn't come from volcanoes. It came from a rapid acceleration like this, a runaway train effect. We also know from the fossil record then the temperatures rose by 6 or 8 degrees. And we also know from the fossil record that 90% of the species on Earth at the time couldn't adapt and went extinct. Now, we absolutely do not know that this would happen again. We absolutely do know that there is only one way to find out. Right? So this is why people are concerned about CO2 emissions. We're not concerned about a degree or 2 of warming here or there. We're concerned about fundamentally changing the atmosphere of our planet to a place where no human has ever breathed before. There's also one other concern. We hear about the ozone, and we can fix that by a treaty because ozone is naturally formed and destroyed because it's a reactive molecule. But CO2 is not a reactive molecule. We live in an oxidizing atmosphere full of oxygen, and it's the most stable form of carbon. That means it doesn't go away. The only way to get rid of it is that, of course, plants breathe it, but they unbreathe it because photosynthesis is balanced by humans and respiration. So you can't remove it that way. You can remove it by getting the CO2 into the oceans, but the near-surface ocean takes time to mix with the deep oceans, and that time is understood. And the rate of decay of what we will do in the next 50 years will take 3,000 years. So we can say that what we do in the next 50 years, if we decide to do it, is going to change the atmosphere of our planet for a time scale that I like to say comparable to modern human history. And nobody has a technically credible way of getting rid of the hundreds of trillions of pounds of carbon dioxide that will be distributed throughout our air within our lifetimes. We do not know absolutely what this will do. Some predictions say it won't be, that it might be better in some areas. Some predictions say it might be worse. We do know that if we don't like what we get, it's going to be extremely difficult to foresee how we would change it. So society is going to have to take a risk management issue of whether or not it wants to burn all of that cheap fossil energy and decide that it would be okay to do what is, from a chemist experiment, the biggest chemistry experiment with our planet humans will have ever done. So that's why there's a problem. If you want to change that problem, you can't talk about a few light bulbs in Fresno. And it's not clear, by the way, from policy viewpoints that we as a society have yet expressed the political will to really seriously want to get off of the path we're on. The other thing to understand is because CO2 lasts so long, that if you wait 40 years to do anything about it, you have 40 more years of emissions under your belt that just is not going to go away. So the time to decide for what we want our planet to look like in the next 3,000 years, like it or not, is right here, right now. Right? This is not waiting for the cost of oil to go up and then deciding that we have something else. This is waiting for the cost of changing our atmosphere forever, basically, to be decided by us. If you wanted to stay on that curve that I showed you, when we got the energy levels down to twice it takes to eat, if you want to hold the atmospheric carbon dioxide concentrations to double, still off the chart, what any human will have ever breathed, you need 10 trillion watts. If you want to stabilize it at better than that, you need 20 trillion watts. When people talk about reducing emissions to 90% of 1990 levels, if demand is going to rise, they mean bringing online within our lifetimes at least as much energy from renewables as all the energy we now make from all the oil, coal, gas, and nuclear power plants combined. Because if you're going to substitute energy for the energy you use now, it's got to come from somewhere. That's how much we have to do. So Marty Hopworth said, this is the pitfall of wait and see, because wait and see is wait and do. Right? He also said something I believe. Without policy incentives, this isn't going to happen by itself. Because the lights go on. And everybody just pays a nickel a kilowatt hour, and we're pretty happy. And where in the world would we get 10 to 20 trillion watts of carbon-free power even if we wanted to seriously do it? And he said, we need a moonshot to do this. I'll tell you where you can get all that energy. There are only 3 places. You can get it from nuclear power, I'm personally not for or against nuclear power. It's a societal decision as to whether or not we deploy it. But I told you the scale. Remember that first thing about scale? If you want 10 trillion watts just to hold CO2 levels to double, you need to build 10,000 new nuclear power plants. That means you need to build one every other day in the world continuously for the next 50 straight years, starting today. Actually, starting 5 years ago when I first started to give this talk. And that would hold CO2 levels to off the chart, double, if we conserved energy down to twice as what it takes to eat. If you don't conserve that much energy, you need to build twice as many of these. So you have to conserve energy to make this problem even tractable. But no amount of energy conservation ever put food on somebody's table or ever turned on someone's light bulb. We have to make clean energy too, in very large scale. Oh, by the way, there's not enough uranium on our planet to run that level of nuclear power for more than 10 years. So we could get it, but we'd have to get it from plutonium. So it's a double dare to think about 10,000 plutonium-containing nuclear reactors on our planet and whether or not we would actually decide to go there, starting not 50 years from now, because if we wait 40 years from now, we have 40 years worth of emissions under our belt that is simply not going to go away. You could do it by sequestering the carbon, because we could still burn coal, but let's just put it somewhere where it won't go into our air. Put it in the oceans, but that's been discredited because we know that when you add carbon dioxide to water, you make soda water, and that acidifies the oceans. It'll change the ecosystems when we add the billions of tons every year to the ocean, so we don't want to do that. You could put it where the oil and gas came from in the first place. It's been there since the dinosaurs. It won't go anywhere again. But there's only enough there to hold 50 years at best worth of capacity because you're trading a dense fluid, oil, for a gas, carbon dioxide. It's going to fill up the volume a lot more quickly. You can put it in the underground aquifers, in brine under the ground. And there's thought to be about 100 years worth of capacity there. This is what is behind our nation's #1 energy policy called clean coal. What it means is we're going to find a way to bury billions of tons of carbon every year under the ground. This should be explored because coal is abundant and it will be used, and if it's going to be used and we want to not do this great experiment, we'd better find a way to put the carbon dioxide somewhere other than our air. But there are challenges. The challenges are if 1% of it leaks after 100 years of doing it, then the amount coming out of carbon dioxide is exactly the same as what you tried to avoid in the first place. We know all reservoirs leak. We know CO2's migrated in Lake Nyos, Cameroon, just 10 years ago and killed 1,700 people when it bubbled up off the ground. Those of you that have been to Mammoth know that there are deaths there from CO2 coming up unpredictably. We would have to put enough CO2 under the ground in the United States that would fill a volume equivalent to Lake Superior every single year. And we would have to do that knowing that it won't go anywhere at 0.1% for the next 1,000 years. And then we're going to have to testify in court that we're going to write the environmental impact statement that's going to say, we're going to go do that and nobody's going to sue me if it comes up and kills somebody. Right? We should absolutely be pursuing this. As scientists, we want to understand the fate and transport of CO2 in the subsurface and how we could ever make a statement to the general public that it would be, quote, safe. Right? But it's not a given that it will work technically. By the way, the Department of Energy's goal is to store 1 billion tons by 2025 and 4 billion by 2050. The United States currently emits 1 billion a year. If our goal is to store 4 billion total by 2050, it's a drop in the bucket. So even our goal is not even close to what is needed to avoid these emissions. The third way is to not burn carbon, but to use renewables. And there's some good news in this, because there is a silver bullet or two. But not all renewables are born equal. Hydroelectricity is the best, because it's the one we use the most right now. It's a model renewable energy resource. It's true that when you build a dam in China, you only displace about 1 million people from their homes. And it's true that we have fish dying. But it's also true it's relatively cheap and benign. That means we've used it pretty much everywhere we can use it. In fact, if you added up all the kinetic energy in every river, lake, and stream on our planet combined, it's only worth 4 terawatts, and we need 20. Now, you can't dam up the Okefenokee Swamp and get much energy. So where you can technically do it's only about 1. And where you can economically do it, you could technically dam up the Hudson River, but the Yankees wouldn't make the playoffs then, so we would have to find a new place for them to play. I'm a Red Sox fan, so I wouldn't mind that, but nevertheless. Where you can do it technically is only 0.9 terawatts. We've maxed out on hydro. It's good to talk about, but there's no room to grow. We hear about geothermal. There are a few places where nature's kind to us and hot steam just comes right up from the ground near geysers. But we know the temperature of the core of the Earth, and we know the diameter of the Earth, and so we know how much heat gets to the surface. And the total that gets there is only 57 milliwatts per square meter if you multiply by the area of all the land on our planet. If you could get it all, which you can't do according to the second law of thermodynamics because it's a small temperature difference. But if you chose to cover every square inch of all the land on Earth at 100% efficiency, you'd get 11 terawatts. We need 15 to 20, and you can't even get close to this, and we're not going to cover all the land on our planet. So the heat of the Earth isn't close to satisfying our human thirst for energy. Wind is the fastest growing renewable, and that will continue for a while because we haven't milked all of the windy sites. People don't like them because they look ugly. Every energy source has some issues. If you add up all the energy available and all the wind on our planet in the windy areas combined, if you built 2 million state-of-the-art wind turbines, you might get 2 trillion watts. That's a good thing to do because it's economical to do it in certain places, but it's easy to show, and I teach every freshman chemistry here. I've done it for the past 2 decades. It's easy for them to show that the energy in the wind goes like the cube of the wind velocity. And that means that if you build a windmill and the wind speed goes down by a factor of 2, the energy you produce goes down by a factor of 8. And that's why you only put it in the highest windy areas. That's the only place you can pay it off. You can't do it on your own home because it's not windy enough like it is in the San Gorgonio Pass to make it economical. We hear about ocean energy. Here's a logarithmic scale. Here's all the energy in all the ocean currents, tides, and waves combined. They're not even close to 1 terawatt, and we need 10 or 20. It's not close. We hear politicians talk about, we put up a new ocean thermal energy plant in the blah, 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 and we made 100 megawatts. But we need trillions of watts. We hear a lot about biofuels, and Chris Somerville, an esteemed developer of biofuels, will be visiting us in January as part of the next popular Chen Wang Energy Seminar series that we're having, and I invite you all to come. Biomass is a good thing to do because it uses the sun, but plants themselves are fundamentally inefficient. Plants are beautiful to look at and they're green. Anybody that's seen a solar cell knows it's black. Plants are the wrong color to absorb all the sunlight. Nature didn't design them to be energy conversion machines. It designed them to reproduce and do other things. They get enough energy to do what they need to do. And in fact, they saturate at 1/10 of a sun. When it gets too bright, they turn off because they would have radical damage, just like sunburn, if they continued to use all of that. They couldn't use it fast enough. And photosynthesis rebuilds itself every 30 minutes anyway. Part of the energy used in a plant goes into the living of the plant and keeping its machine running and rebuilt. A lot of it does that. And so the fastest growing plant, it turns out, only uses 0.3% of the energy of sunlight that hits it. And that means you need to cover very large areas to get a lot of energy. And we'll have to practice agriculture on the scale of agriculture. Right? In fact, if you take all the land where you could grow crops on our planet, and you subtract off, that small amount that we use to grow food for the people that need it, and took all the rest and planted it with the fastest growing crop, and assumed that you put no energy into the farm and you wasted no energy taking the fuel out, you got it all, you might get 5 trillion watts. Now that's good in that if you got 2 or 3, those are valuable fuels. And so they can be a significant player. I'd rather have 2 trillion watts out of something than 0. It's the only big number so far. So it's definitely worth doing. But you shouldn't look to biofuels to supply all of our energy either in bridging this energy gap because of this fundamental limitation. Oh, by the way, just to give you a calibration, last year, the numbers are that 20% of our corn produced 2% of our transportation fuel. We have a law going through Congress, a law of Congress, not a law of physics, that says that we're going to up that by a factor of 5 within 5 years. Well, that's going to take 100% of our corn to offset 10% of our transportation fuels. Do we want to do that? And by the way, it uses almost as much energy from coal as it produces in the ethanol that is made. I promised you that not all were created equal because there is one really big number. The sun gives us not tens of trillions of watts, but 120,000 terawatts all of the time. Plants only use a tiny fraction of it, so we have to cover very large areas. But if we could use even a tiny bit more, we could get all the energy that you could conceive of using. In fact, more energy from the sun hits the Earth in 1 hour than all the energy consumed on our planet in an entire year. Nothing else is even close. In 1 year, more energy from the sun hits our Earth than all the oil, coal, gas, nuclear power ever consumed by humans combined in history. Right? So now you know why I work on it. Because the numbers say if you want to make a big difference, you should work on solar energy. Because it's the only energy source that if we can find a way to really capture, convert, and store it, can make the big difference, which is where we have to go. Unless we decide we want to build 10,000 nuclear power plants. Photosynthesis right now gives us 90 trillion watts, and we only need 10. We can't have that because it's in detailed balance with respiration. We just need to find a way to get 10 more. If you took 10% efficient solar cell equivalents, not 0.3% like plants, this is the amount of area you would have to cover to supply all the United States' energy forever. The bad news is it's not a small area. It's at a representative mid-latitude. I didn't just put it in the deserts. It'd be a little bit smaller than that by kind of a square root of 2. It's 10 times bigger than everybody's roof. Right? It's equivalent to the nation's numbered highway systems. Good news is I've never met anybody that actually lives there. That box, maybe Google Earth has some house there, but they don't like it when I tell them that. Joke. You'd never do it that way. You distribute it all around the country, right? You would just not put it there, but it gives you a feeling. It's not a small project. In fact, the only things that we make in enough area this isn't 100 roofs. This is 1 million roofs a day, every day for the next 50 years, just in the United States. So when we hear about California doing 1 million solar roofs in 10 years, that's a good step forward. But we need to do 1 million solar roofs a day, every day. If we wait 5 years, we're 1 billion solar roofs behind schedule. Okay? This is why people like us have to be figuring out ways to make solar cells that are as cheap as painting your house or rolling it out on your roof like carpet. Because if you have to have people pounding them up there, we don't have enough people, we don't have enough money, we don't have enough time to get from here to there. There'd be 6. If you wanted to put 6 boxes, you could power the planet forever. We all know one big problem with solar cells, they just cost too much money. In fact, the cheapest you can buy them now is 25 cents a kilowatt hour, but SCE will sell you electricity, they make it at a nickel a kilowatt hour. And even that's expensive energy because they put in coal or natural gas and their boilers are only 30% efficient. So for every 1 watt that comes out, they have to put in 3 watts in the first place. Right? And in fact, we know how much energy is going to be in the sun for the next 30 years. It's not going to shine any less. So if I give you a square meter of land, and I tell you I'm going to get 10% of the energy out for you on average every day and every night, and now you go sell it, but break even because it's going to cost you $300 a square meter to put it up there in the first place, and another $300 to get it installed. Just for you to sell it to me and recover your initial costs with no interest, you have to sell it to me at 25 cents a kilowatt hour. But I'm paying a nickel a kilowatt hour for it out of the plug. Not too many people in developing countries are going to pay that price. You cannot get there just by improving the efficiency. That's a good thing to do. But you can't get off this cost per watt curve to where we need to go without really lowering the cost to something like $50 or $100 a square meter. $10 a square meter is a good target. The cost of paint at Home Depot is $1 a square meter. The cost of this carpet is $10 a square meter. So whatever stuff we make can't cost more to install than paint or carpet. Then you have something. So we're working on solar paint. We're working on taking little particles that are the pigment in paint and linking them together. The problem with doing this is that scientists have tried to do this before, but when this material absorbs sunlight, if it's a single crystal, like a silicon chip in a silicon photovoltaic cell that goes on your roof, it has to be very pure because it needs a certain thickness to absorb the sunlight. And if it's not thick enough and pure enough, it won't absorb the light. And if it does, it'll just be blacktop and not make anything but heat. It can't make electricity unless the electricity can make it all the way through to the wires. And the problem is, if it's not very pure, it's just going to make heat. It costs a lot of money to make a very pure piece of silicon the size of your roof. When you just take little particles, they're cheap. But the electricity that's made on each particle can't hop from particle to particle, from stepping stone to stepping stone, so it just makes heat. But there's no law of physics that says this has to be. We just haven't yet figured out how to fool the atoms at the surface of every one of these particles into thinking that they're not at the ends, but that they're in the middle. That's what chemists and material scientists are trying to do, to link them together in a way that this is just like a binder in paint, when the pigment is the colored stuff, except instead of just paint, it's paint that absorbs sunlight and makes electricity instead of just black stuff making heat. So we're working on this. There's another way. Maybe you could make trees. After all, nature made trees as a way to absorb sunlight, and it's pretty smart. The reason it's pretty smart is because it can have a very long depth to absorb light, and instead of having to move the electricity all the way from the bottom of the tree to the top, where it's nutrient, it moves it sideways through the bark. So it moves it over a much shorter distance in a narrow diameter tree than the height of the tree. And that's smart, because this material can be really not very pure, and the electricity that would have been lost had it had to go all this way can be collected because it only went a little bit sideways. So you can have a very tall tree that's very narrow, kind of like the beautiful aspens that grow in Colorado. That's a great design. I saw those aspens, and Harry Atwater and I launched a joint project to make nanometer scale aspen solar trees. And that's what we do. So we have beautiful pictures now of rods that we're growing in the lab that are out of very cheap material that all point toward the sun like aspen trees or blades of grass that allow us to use much cheaper material than we could use before in order to collect sunlight. We even have them in a piece of plastic that can be rolled out now. So we're really excited about that. We just did that last month. They're not on a solid substrate anymore. They're literally transferred into a piece of plastic. It's fish tank goop. It's the stuff you use in the fish tank, and we can roll it out. We can't yet make much electricity out of it, but we're trying. But even if we succeed in making a lot of electricity, we already discussed in the initial group that our work would not be done. Because there's one little problem with using the sun to power our planet. It's got a little nasty habit. It locally, last time I looked, goes out every single night. Right? And we need energy all of the time. Johnny Cochran, if Johnny Cochran were interested in energy, he would say, "He that cannot store shall not have energy after 4." Right? You can never run an economy on an intermittent source that goes out every single night. It's good for peak shaving, for saving energy in the summertime when we get a lot of electricity resources in California and avoiding air conditioning, that's good. But you can't run your cars off of it, and you can't heat your houses off of it in the winter time, and you can't do anything at night unless you find a way to store it cheaply. And there's no good way to store massive quantities of electricity. If there would be, you should do that right now because we pay 30 cents a kilowatt hour in the middle of the summer, and at nighttime we pay a nickel a kilowatt hour. You should buy it at night and sell it in the daytime to all your friends and laugh all the way to the bank because you stored it cheaply. The cheapest way is pumping water uphill. And you can do that by filling a reservoir every winter and emptying it every summer. But you can't do it every day and every night, filling up Lake Mead. And in fact, the energy in pumping water uphill is so low compared to the energy in gasoline. For every gallon of gas that you burn, you would have to move 50,000 gallons of gallons of water up the height of Hoover Dam, just to store the energy in 1 gallon of gasoline. Right? So there isn't enough water every day and every night to do that. What works well in a city doesn't work well in a country. We have to make chemical fuel. Nature figured that out. Stores the energy in chemical bonds. So we're trying to do that. We know bugs know how to do it. This little bug, this hydrogenase bug, it takes sunlight, and that molecule, that enzyme, converts that not to electricity, but it makes hydrogen. And of course, there's another enzyme in photosynthesis that lets plants breathe out oxygen. And there's another one that lets it fix carbon dioxide out of the air to make fixed carbon. Now, with X-ray structures done by people like Doug Reese at CalTech, we now know the structure of these molecules for the first time. And we know what the atoms are that do the activity that power life on Earth. And our job as chemists is to pull out those key pieces and put them in with our things that really cheaply make electricity, and not make electricity, but directly make stored chemical fuel. Because that's what people really want. What we really want is something that will store the energy so that we can go to the gas station or we can go to our home and turn on that switch day or night and get energy whenever we need it, whenever we want it. And the only way you can do that at scale is to make a chemical fuel. Nature figured that out. That's what photosynthesis is. So we're trying to build this part of a leaf that's got a membrane, that's got our grass and trees in it on the nanometer scale. And then instead of just making electricity, we want to directly make chemical fuel so you can burn it later on to get hot water or to run your car or to do whatever else we want to do with that energy. We don't know how to do that yet, but we're working on it. So finally, I think by now you see why people like me care so much about this problem. We're going to need more energy, and by the way, if we didn't need more energy, instead of increasing the rate of energy demand, if we kept it flat, And in human history, there's never been a year in which we used less energy than we did in the year before. Even if we held it constant, because unfortunately CO2 lasts for thousands of years, the day at which we doubled would just change by 10 years. So it would be 2060 instead of 2050. You can't will yourself out of this problem. That means we've got to find a way to capture, convert, and store energy from the sun cheaply so that not just developed countries can afford it, but developing countries can afford it too. You can't do anything without energy efficiency, because if we don't find ways to more effectively use energy and conserve it, then the problem of supplying the amount we need is so hard. We need the equivalent of a nuclear reactor every couple hours. It's not going to happen. So no rational energy program doesn't start with clever money-saving and good ways to save energy, from building design to better cars to ventilation and everything in between. That's, by the way, good for both of our causes, both energy security, because if you save energy, you have to import less, and environmental security, because if you save energy, you don't emit as much product. There's nothing bad about it. And so it's obvious that that's the first step where there's low-hanging fruit. But in addition, we need to make a lot of energy. And there are only 3 cards we have. And one is to bury that carbon somewhere, if we dare, to build 10 or 20,000 plutonium-containing nuclear reactors if we double dare, or to find a way to use the biggest resource that nature gives us, which is the sun. We've got to make it really cheap, and we've got to store it, or we don't have much. So that's the one that we're working on here. I haven't talked about policy. In the policy arena, everyone wants to know how much it'll cost. How much is it going to cost? But there are, I think, bigger picture issues. One is you can always say it'll cost money, because it will. We have a mature, incredibly efficient energy economy. It's been going on for a century, and we've learned how to do oil production and gas production and coal. We learned how to use it effectively. And it's unrealistic to expect that any new technology is going to come in at the bat that's going to cost as little as something that we've worked on for 100 years that's in everybody's home. It's going to cost money. And you can say we can't afford to do this. That's one extreme. The other extreme is you can say we can't afford not to do it. Because think about the alternative. And real life is in the middle somewhere, probably, and policy is way above my pay grade. So I don't get there, but our job is just to say, if you decide to take this path, this is what's going to happen. And if you decide to take that path, that's what's going to happen. And then we have to decide on which path we want to put our planet. Of course, we need to commit, because it's nice to talk about saving energy, but talking about it is different than doing it. And it's nice to talk about making a little energy, but we need to put on the equivalent of a nuclear power plant a day or 1 million solar cells a day starting today, or find a way to really lower the cost so we can do it faster, better, cheaper later on. And that's the challenge that people like us are working on, because we should be working on ways to really lower the cost of getting clean, cheap energy to everybody, not just those that can afford to do it in California in the summertime with what we have now. That's the challenge for scientists and engineers. That's why Rick Smalley said that he thought this was the greatest challenge, because Rick used to tell me, and I agree, that cancer is a tragic disease, of course. Actually, my wife lost both her parents to it, and I lost my dad to it, and so we know how tragic that is. But like it or not, if we don't cure cancer in 50 years, the world's going to stay the same. If we don't build the next nano widget in 50 years, it may not be a better place. I won't have my cell phone giving me the internet, but the world's going to stay the same. But we can say, like it or not, as scientists, because CO2 lasts for centuries to millennia, that if we don't fix this problem within the next 50 years, that it's just true that the world is never going to be the same. That's why people like me work on this problem.